All right, from here we've got to take a little bit of an in-depth look at our atomic orbitals, specifically the s and p orbitals. You might recall from Gen Chem that your 1s orbital, and s orbitals in general, are spherical shaped here. The only difference between the 1s, 2s, 3s, so on and so forth is you end up having radial nodes for the bigger ones, but for the 1s orbital here, no nodes whatsoever. So, and then for the 2p orbitals, so they all have a node at the nucleus here. You see right at the nucleus here, that's what we call a node. And we'll find out that's where the wave function goes to 0. So these lovely shapes come from what we call wave functions. We use the Greek letter psi here to symbolize wave function. So the wave function for a 1s orbital is this lovely equation right here. And technically, either the positive as you see it or the exact negative of this, they're both solutions to the Schrodinger equation and the wave function of a 1s orbital. So the 1s orbital, turns out, can have all positive values or all negative values, but it is a function that never actually will ever equal 0. So what you're actually plotting here for 1s orbital is what we call the 95% probability. So if you look at the region of space that this equation describes, so it turns out that it goes out to infinity. It asymptotically approaches 0 as you go to infinity. So we can't really plot the whole thing in a three-dimensional representation here, but to the 95% probability, it'll occupy this region of space just, defined by this sphere. So for the 2p orbitals, there's 3 of them again. So one on the x-axis, one on the y-axis, one on the z-axis. So, and they have 3 slightly different wave functions. One of them is this one you see here. So, and the big thing I want you to see here is that r is a part of the function here, not just in the exponential, although it's there as well, but r is a part of the function. And that is why if you have a radius of 0, you get the whole function goes to 0, because anything times 0 is 0. That is why there's a node at the nucleus of every single p orbital. So it turns out the entire wave function includes the term r multiplicatively, and therefore goes to 0 when you have a 0 radius. So all of these have a node at the nucleus. So these are the wave functions, again, plotted at 95% probability. You should know these general shapes. You should also know what we term the probability function. So and the probability function is just the wave function squared. So if I told you that I had a 50% chance of winning the lottery today, you'd be like, go play, Chad. 50% chance, that's really good odds. So, but if I told you I had a negative 50% chance of winning the lottery, that might be a little bit confusing because you can't really have a less than 0 probability. So there's no such thing as a negative probability. And so because wave functions have regions where they're both positive and negative, that's what this difference in shading for the p orbitals is. One side is positive, one side is negative, and it could go either way. So either orientation. So we just have 2 different forms of shading, either shading and no shading, or blue shading and green shading, or just some difference in shading pattern we often use to represent that one's positive, one's negative, but we just never define it. So because wave functions can be both positive and negative, they can't represent probability, but the probability function, the wave function squared is the probability function. If you square a positive number, it's still positive. But if you square a negative number, it also is positive. And so if you square the wave functions, so like the 1s orbital here, or the 2p orbital here, so they're all positive. Well, the 1s was positive anyways, or at least all positive or all negative. So now with the wave function squared, it's definitely all positive. And for the 2p, it's all positive. There's still a node, because 0 squared is still 0, so still a node at the nucleus, but it's all positive. And this is actually what we use to describe the probability function, the probability of where you'd actually find an electron. So just want to be sure the difference here between the wave function and the wave function squared. So now that we've reviewed the shape of the s and p orbitals, let's talk about valence bond theory. So valence bond theory says that the nature of a bond is that you have overlapping orbitals from 2 adjacent atoms. So, and it turns out this can happen in one of 2 principal ways. We talk about sigma overlap, and we talk about pi overlap. So sigma overlap occurs in all single bonds. All single bonds, you have end-to-end overlap of 2 orbitals, and it can be any 2 orbitals, s's, p's, or even hybrids. So here's a couple of s's, here's a couple of p's, here's an s and a p, here's a hybrid and s, or 2 hybrids. We'll talk about what hybrid orbitals are here in a little bit. But end-to-end overlap of any 2 orbitals is termed a sigma bond, and all single bonds are sigma bonds. So if we look at this structure here, that single bond is a sigma bond, and that single bond is a sigma bond. So, but a pi bond is something unique and something special. So if you look at pi, that's a letter in the Greek alphabet. So the Greek alphabet and the English alphabet both come from the same derivative root alphabet, and they both have kind of analogous letters. And the Greek letter pi corresponds to the English letter p. And we use the Greek letter pi because a pi bond is the side-to-side overlap here of p orbitals. So it's always side to side, and it's always p orbitals. At least that's the only type you'll ever study in organic chemistry here. So again, sideways overlap of p orbitals. And you're only ever going to see a pi bond in a double or a triple bond. So it turns out that two atoms only are ever going to have one set of orbitals pointing towards each other. So, and the ones that point towards each other are going to form a sigma bond. But any additional bond after that has to be this sideways overlap of pi orbitals. So when you have a double bond, the first one's a sigma, the second one's a pi. And when you have a triple bond, the first one's a sigma, but the other two are both pi bonds, side-to-side overlap of p orbitals. So again, these are your two principal types of bonds. You should know how to recognize them from a structure here. And again, all single bonds are sigma bonds. A double bond is 1 sigma 1 pi, and a triple bond is 1 sigma and 2 pi bonds. So we just briefly mentioned the idea of hybrid orbitals. A hybrid is just a combination of two orbitals. Notice a hybrid car can work on both electricity and gasoline. Hybrid orbitals are just combinations of orbitals to form a brand new type of orbital we call a hybrid. And the three types you got to be familiar with in organic chemistry are sp hybridization, sp2 hybridization, and sp3 hybridization. And it turns out as long as you can determine the number of electron domains around an atom, there's a real simple quick formula for getting the hybridization as well as the geometry and the bond angles. So if something has 2 electron domains, that atom is sp hybridized, and the bond angles around it will be 180 degrees. If an atom has 3 electron domains, it is sp2 hybridized, and the bond angles around it will be 120 degrees. And if an atom has 4 electron domains around it, it'll be sp3 hybridized, and the bond angles around it will be approximately 109.5 degrees. Now we got to understand here that an electron domain is one of two things. It's either a bonded atom, and again, I don't care if that's a single bond, a double bond, or a triple bond. Every atom bonded is a single electron domain. So, or it's a lone pair of non-bonding electrons. Those are our options here, and by simply determining the number of electron domains, you know the hybridization and the bond angles. Now, we haven't really even explicitly shown what hybridization is, but you should be able to determine it based on a structure. So if we look at this carbon atom right here, he's got 4 bonding domains, so 4 atoms he's bonded to, no lone pairs, and so 4 electron domains makes him sp3 hybridized. So if we look at the nitrogen right here, he's got 1, 2, 3 atoms he's bonded to, plus that lone pair for a grand total of 4 electron domains again. Sometimes we call that the steric number. And with 4 electron domains, or a steric number of 4, again, that makes the nitrogen sp3 hybridized. If we look at this carbon atom right here, he is bonded to 1, 2, 3 atoms. So notice the double bond is still just a single domain. It's just one atom up here, one oxygen he's bonded to. So he's bonded to 3 atoms, no lone pairs. That's a steric number of 3, or 3 electron domains, and he is sp2 hybridized. In the next structure here, we've got a couple of different atoms we can, actually we could have done the same thing here. So oxygen here is bonded to 1 atom, plus he's got 2 lone pairs. So the oxygen itself with 3 electron domains is also sp2 hybridized. And then in his next structure, we can assign hybridizations to a few different atoms. This carbon right here is bonded to 4 atoms, no lone pairs, so he's sp3 hybridized, a steric number of 4. This carbon right here is bonded to 2 atoms, and again, I don't care that it's triple bonded to the nitrogen. That's still just a single atom bonded to. So 2 atoms bonded, no lone pairs, with a steric number of 2. That's an sp hybridized atom. And the nitrogen here is bonded to 1 atom, carbon, and 1 lone pair. So with 2 electron domains, he's also sp hybridized. So that's kind of how you determine hybridization just by looking at the structure, but let's take a little bit deeper look on what hybridization actually is. So hybridization here, like we said earlier, is a combination of orbitals. And it turns out, again, these orbitals are described by mathematical equations we call wave functions. And it turns out you can combine those wave functions. So in this case, we're going to mix an s and a p orbital. So if you recall, the s orbital is either all positive or all negative. I'm just going to say that this, let's just say this corresponds to all positive. Whereas the p orbital has a node at the nucleus, and one side's positive, one side's negative. So here I've got shading corresponding to positive, non-shading corresponding to negative. Same thing over here. So, and if we look here, when we combine hybrid orbitals here, we can have something called either constructive or destructive interference. So, and you might recall, like with a simple sine wave, so one part of the sine wave is positive, one part is negative, and if you have another sine wave there right next to it, where the positives overlap and the negatives overlap, the result is you get an amplified sine wave. That's what we call constructive overlap. Destructive overlap, on the other hand, so again, another sine wave. Again, part of it takes on positive values, part of it takes on negative values. if it is overlapping with another sine wave exactly out of phase. Here where the positive part overlaps with the negative, and here the negative with the positive, they cancel, and that's called destructive overlap. Well, the same thing can happen with these three-dimensional wave functions here. If positive parts overlap, you get constructive interference and it amplifies it, whereas if a plus and a minus overlap, that's destructive interference, and they're going to do the exact opposite of amplification. They're going to kind of cancel each other out to a certain extent. So if we look here between the s orbital and p orbital on the left here, on the left-hand side, they're going to amplify each other, and that's why this region got bigger. Whereas on the right-hand side, plus with minus, they're going to cancel each other out, and that's why this region got smaller. But we mixed one s and one p orbital here, and we form an sp hybrid. So same thing on the other side. It turns out this could happen in one of two orientations, and both happen simultaneously here. So in this case, it's the right-hand side where plus overlaps with plus, and so that region is amplified. And on the left-hand side, plus with minus happens there. So and that gets minimized as a result, or reduced. So another sp hybrid. And if you kind of look at the orientation here, we have these two sp hybrid orbitals, and let's just say this happened for a carbon atom. You'd have one with its big lobe pointing towards the right, the other with its big lobe pointing towards the left, and they would magically be 180 degrees apart here. So, and something that is sp hybridized has two electron domains, and they're going to be 180 degree bond angles. We can see that those angles work out perfectly, and that's one of the big things this idea of hybridization has going for it, is it allows us to predict bond angles to a very good degree. So this idea of hybridization allows us to predict proper bond angles here. And we'll see why this is important, because if we just use the regular atomic orbitals to form bonds, we wouldn't get the appropriate bond angles. So if we look at kind of carbon's valence electrons here, and carbon is 2s2, 2p2 in his ground state. There's this valence electron configuration. Well, it turns out he's only got these two unpaired electrons, and it's typically the unpaired electrons that are used to make bonds. So the first thing that happens is a promotion. Carbon's going to take one of these s electrons and promote it up to the 2p. That way he now has 4 unpaired electrons and can now make 4 bonds. So a little bit of an energy investment, but every additional bond lowers the energy significantly of carbon's electrons here. So we do have a problem, though. If we look at carbon here, if he's got a p orbital, and let's say we look at the vertical p orbital, and another p orbital here, we look at the horizontal p orbital, and if these are what are overlapping with the s orbitals for hydrogen, at least for 2 of the hydrogens, say in a molecule of methane we've got diagrammed here, we'd find we have a problem. So the p orbitals are on orthogonal or perpendicular axes, and so your bond angle here between the hydrogens would end up being 90 degrees. So we definitely know that the bond angles in methane are not 90 degrees, they are 109.5 degrees exactly. So, and they are all 109.5 exactly, and so we figure out that carbon must not be using his regular atomic orbitals to make his bonds. So it turns out what carbon is doing is he's taking the wave functions for all of these s and p orbitals, and combining them. And it turns out if you combine 4 orbitals, there are 4 different ways you can combine them. And so by combining those 4 orbitals, those 4 wave functions, you create 4 brand new wave functions that are combinations of s and p. And they're 1/4 s and 3/4 p, and it creates 4 brand new orbitals. We don't get crafty on how we name them. We just call them sp3 hybrids based on what we combine to make them. They all have 1 electron in them. So, and magically, if we look at kind of diagram these out for carbon, they kind of look like elongated p orbitals that are a little fatter than normal on one side, a little bit truncated on the other side. So, and I'll draw 2 of them on this carbon atom here. So, and they're going to overlap with the s orbitals for hydrogen here. So, and magically, this bond angle right here between them is 109.5 degrees. So, and I'd have a tough time drawing the other 2 for this bond to this hydrogen and this bond to this hydrogen, because the wedge here means out of the plane and into the plane. It's 3-dimensional, and I suck at drawing to begin with. So I'm definitely struggling to draw something into 2 dimensions, let alone 3. So I'm not drawing those other 2 sp3 hybrid orbitals, but they definitely exist. They're all 109.5 degrees apart. This idea of hybridization allows us to explain bond angles that the original atomic orbitals here, like with the p's, doesn't allow us to accomplish. So now let's kind of take a simultaneous look at all the options available to carbon. Carbon can end up being sp3, sp2, or sp hybridized. And the first thing carbon's going to do in any case, again, is promote one of his electrons from the 2s up to the 2p. That way he ends up with 4 unpaired electrons and can make 4 bonds. But again, we're not going to end up with the proper bond angles in any case if we just use the atomic orbitals. We saw in methane, the angles want to be 109.5, not 90 degrees. So in the case of formaldehyde here, we can see that carbon's got 3 electron domains. And with 3 electron domains, the bond angle should end up being 120 degrees. Again, not 90 like you'd if you use the p orbitals. And same thing here in hydrocyanic acid. Carbon here has got 2 electron domains, and so the bond angle should end up being 180 degrees. Again, definitely not 90. And so this idea of getting these appropriate bond angles can be explained perfectly with hybridization. So if we kind of look at the way this works, we already kind of talked about sp3 and methane on the last slide, but we can talk about being sp2 hybridized. So in this case, with 3 electron domains, that means that this carbon atom right here needs 3 hybrid orbitals. To make 3 hybrid orbitals, he needs to mix 3 atomic orbitals. And the first 3 available are an s and 2 of the p's. And so this carbon's going to take and mix the wave functions of all 3 of those orbitals. If you mix 3 wave functions, you create 3 brand new wave functions. And that's why he creates 1, 2, 3 brand new sp2 hybrid orbitals. And these sp2 hybrid orbitals, so there's 1 there, and 1 there, magically all point 120 degrees apart. So you'll also note, though, that this carbon still has an unhybridized p orbital, so which he definitely has to have. If you look at the bonding here, we've got 2 single bonds, and those are sigma bonds in formaldehyde. So, but with a double bond, one of those is a sigma, if you recall, and one of those ends up being a pi. And a pi bond, that's what we need these p orbitals for. In this unhybridized p orbital, both the carbon and the oxygen have that unhybridized p orbital, so that we can get the sideways overlap here of those p orbitals and form that pi bond. Our last option here, so for sp hybridization, as we'll see with carbon and HCN here, carbon in this case is only going to mix 1 s and 1 p orbital. And we kind of showed exactly how that worked, and we form 2 sp hybrids that point exactly 180 degrees apart. So 1 for bonding with the hydrogen, and for carbon's sake, 1 for bonding with the nitrogen, forming that sigma bond. So, and in this case, again, carbon here, all single bonds are sigma, but out of the triple bond, one of them is a sigma. So, but 2 of those bonds end up being pi bonds. So he has 2 pi bonds. And if he has 2 pi bonds, he's therefore going to need 2 unhybridized p orbitals here. So mixing the s and the p formed the 2 sp hybrids, but he still has 2 unhybridized p orbitals, 1 for each of the pi bonds, 1 between these p orbitals here. So, and the other, we can kind of see the perpendicular one, and I'm going to avoid drawing this. My drawing is just going to get ugly. But you get sideways overlap of those p orbitals as well. So one, and they're in perpendicular planes. But that's your triple bond. So, and these are your 3 options for carbon, either sp3, sp2, or sp hybridization with bond angles of 109.5, 120, or 180.